Hello learners and welcome back to VLSI Simplified. So today we are diving into something really important and often overlooked when starting with Verilog. So that is abstraction levels. Now, if you have ever wondered how we go from writing a few lines of code to building actual hardware, or why Verilog sometimes feels super low level and other time incredibly simple, then this video is exactly what you need. We are going to break it all down from transistors to logic gates, and you will see how Verilog lets us describe hardware at different levels of detail depending on what you need. And hey, by the end of this video, you will even write AND gate using both switch level and gate level modeling just to see the contrast in action. So grab your curiosity, maybe a notebook, and let's get started. By the end of this video, you will not only understand what abstraction means in the world of hardware, but you will also be able to differentiate between switch level and gate level modeling. And you will know when each level is used and what kind of control it gives you. Even write your own AND gate using both transistor and gate primitives. So, if you are someone who is just stepping into Verilog or trying to connect theory to real design, then you are in the right place. Alright, this is VLSI Simplified. Let's get started and let's simplify.
Feel me like a Hellcat.
Chips today are incredibly complex. They power everything from smartwatches to AI systems. But these tiny pieces of silicons contain million to billion transistors. So trying to design all of that at once, especially at the low level, would be nearly impossible. And that's why abstraction is essential. So abstraction allows us to look at the design one layer at a time. So for example, when designing a logic, we don't have to worry about transistors behavior. When designing a data flow, we don't need to manually place gates. And Verilog supports multiple abstraction levels, and that helps us to manage this complexity in a structured way. So at the switch level, you will describe actual transistors. At the gate level, you define how logic gate connects. At the behavioral level, you will describe how the system should behave in response to inputs. And at the RTL, you focus on how data moves between registers under a clock. So each of these levels serves a unique purpose, and together they form the foundation for efficient digital design. Now let's relate this to something we all understand with a real world analogy. Let's make this easier with a real world analogy that is something we can relate to building a house. So think of a switch level as dealing with wires and plumbing. So you are connecting each wire or pipe manually. It's low level, detailed, and not something you want to do unless absolutely necessary. So the gate level is like laying out the walls and rooms of the house using bricks. So you know how things are structured, but you are still close to low level. Now comes to RTL level. This is where you decide how things flow. When you flip a switch, the lights turn on. Or when you turn the tap, water flows. You don't care about pipes, just how things move from one point to another, that is the focus. And finally, the behavioral level. This is like saying, when I walk into the room, the light should turn on. So we're only focused on the expected behavior, not how it happens internally. So abstraction in Verilog works in the same way. So every level hides unnecessary details so you can focus on the logic that matters at that stage. Now that you have seen how abstractions helps in simplifying design, let's take a look at the different abstraction levels supported by Verilog. We will start from the lowest level, the switch level, where you describe your circuit in terms of individual transistor using primitives like NMOS and PMOS. Then comes to the gate level where you describe your circuit using logic gates like AND, OR, NOT and other gates. It's still close to the switch level but more manageable. Next is the behavioral level where you are focused on what the system should do using constructs like if, case, for and so on. It's great for modeling logic quickly and clearly. And finally, the most important one, RTL or register transfer level. So this is where you describe how data flows between registers under the influence of clock. It is the most widely used abstraction level in real world designs and it is synthesizable into actual hardware. In the next slides, we will go through each of these levels in detail along with the examples for the same design. So you can see how approach changes at each level. Let's begin with the lowest abstraction level, switch level. So in the switch level modeling, we describe a circuit using individual transistors. Verilog provides primitive elements like NMOS, PMOS to model how real hardware behaves at the transistor level. So this type of modeling is very close to physical design. It's like describing every wire and switch on a microscopic scale. So we'll usually use switch level description in educational examples or when someone is modeling a custom cells like SRAM bit cell or a latch. However, it's important to note that switch level code is not synthesizable. It cannot be converted into gates or mapped onto a FPGA or ASIC using synthesis tools. It's only useful for functional simulation and understanding low level operations. In the next slide, let's look at how we can implement AND gate using switch level modeling. So here's how we can write an AND gate using switch level modeling in Verilog. We first define VDD and GND, that is ground, using the supply 1 and supply 0 keywords. So they represents power and ground. Then we use PMOS and NMOS primitives to build the logic. The PMOS transistors are part of the pull-up networks and the NMOS transistors form the pull-down path when both A and B are high. Notice how we have to manually wire each transistors. This gives us full control but also much more tedious compared to higher levels. Also keep in mind this level is just for simulation and learning purpose. In the real world design, we typically don't write logic at a switch level. Next up is the gate level modeling. In this level, we describe digital logic circuits using basic gate primitives. Things like AND, OR, NOT gates and so on. So these map directly into hardware components into a chip. So gate level modeling is closer to real hardware than behavioral or RTL. So you are not dealing with the transistor anymore, but you are still manually building logic gates. In the real world design, we don't usually write Verilog at gate level by hand. Instead, gate level netlists are generated automatically after synthesis from RTL code. But this level is very useful for post-synthesis simulation and timing analysis, especially when you need to verify how a design behaves after it's mapped to logic gates. And yes, gate level modeling is synthesizable, but again, we usually let tools handle. And here's what a gate level AND gate looks like in Verilog. We use Verilog's built-in gate primitives and in this case AND that connects the input A and B to produce the output Y. It's that simple, just one line. This style is direct and structural. So you are telling the synthesis tool exactly what kind of gate you want and how it should be wired. Again, while this is synthesizable, it's not common to write full designs this way by hand. Instead, gate level models are usually auto-generated from RTL during synthesis. Still, it's helpful to understand this level, especially when you are debugging timing and doing gate level simulations. Verilog doesn't stop at just AND gate. It provides a variety of built-in logic primitives And here's a quick reference for them. While you probably won't be writing full design using just these gates, but they are extremely useful for netlist level simulation, custom logic blocks, and post level debugging. And that's brings us to the end of part 1. So we started from the very bottom, transistors and gates, and built a solid understanding of how Verilog models real circuit at those levels. But trust me, this is just the foundation. So in the next video, we are going to level up, and it's where the things start to feel a lot more powerful and practical. We will explore behavioral and RTL modeling, and you will see how Verilog goes from hardware heavy to designer friendly. Make sure to like, comment, and subscribe so you don't miss our upcoming videos. I'll see you in the next video. Bye.